Okay, 7, 8, 9, I hope for layups. What'd you get for 7? 12. Okay, cool. What about 8 and 9? 17 thirds? Okay, any questions with those three? Okay. Um, the last one is more of the work justifying the answer. What's the big idea? Take the limit of all of them. The squeeze theorem. As x goes to 0. If you want the limit, that's the question. Then it looks something like this. Now, what is the limit as x goes to 0 of absolute value of negative x? 0. So our answer is between 0 and 0, so it must be 0, right? So the 0 is your answer. Cool. With that work. If you didn't put that work down, please put it down. All right, this lesson is awesome, so fun. You're going to love it. I would just say, oh no, what do you mean? It's awesome. It's just awesome. Okay, now, here's the deal. Consider if you had this region y equals the square root of x on 0 to 9, yeah? If this region was revolved, so this region here is revolved around this axis of revolution. And you get a three-dimensional figure, yeah? Now this isn't the same graph, I apologize, but if this region was revolved around this axis, then you'd get something like that. Except it would, this is only in this front side. It would go back through Mr. Carlson's room as well, yeah? Okay, now that's called the volume of revolution. Now, in terms of graphing this, when this got rotated all the way back down here, do you agree it would reach a minimum of negative? Okay? And then it would go back through the wall. So if you were to sketch this, you typically graph a reflection. And then you give it dimension by, at the end, putting an ellipse or an oval, I guess. So, yeah. Now I know some of you are not artistically inclined, and that's a shame because you will be drawing these regardless whether you are or not. But those of you who are artistically inclined, you're going to love it because you're going to think, oh, that's so cool. You do it really well. I love to see people who can draw work on this. So the question of the day is, how do you find the volume of that? Now then, it is not area of the base times the height. But it kind of is. It sort of is, but not really. So these questions, this is the same graphs, but these questions are really meant to guide you there. So what I want you to do is, rather than me say exactly what this says, this is what I want to say. So I want you to read this very carefully and answer each of these questions, and hopefully they will guide you towards how do you find the volume of it. Give it a go, answer the questions, and talk to me when you think you have a theory. Feel free to talk over to Math Amigos after you've given it significant thought on your own. If you really feel like you're getting it, go for it all the way, find the volume and tell me when you have the volume.
Yeah, I'm not either. There's nothing we can do now. They told me to stay with you.
Let me know if you have a theory about what the true perfect volume is. An answer.
I was thinking of that, you know, you wouldn't say infinity. Oh, maybe that color. No, that was. I fixed my device. Yeah, okay, but it's good as oh, you're right, Maddie. I said midpoint, but still I can't.
You should be getting an answer soon.
The limit as x approaches infinity. Sure. Right? Is it the limit as x approaches infinity? Yes.
What are you thinking? Okay. So it may be in this
Wait, we have to sell it on
You'd have to say what's the lowest. What is it?
Get it right on
Small delta X. No. How are you doing? You got an answer? So the infinite, the limit, yes, and that's all true, yes. The limit as the number of rectangles goes to infinity. Of that, what is that in calculus? So you take an infinite sum. what calculus does that.
H goes to infinity.
H, that's an N, sorry.
The height is infinitely big.
The height is not infinitely big, it's the opposite. Okay, as the number of cylinders goes to infinity, what does the height of each go to? Yeah, now the height instead of 3 is 1. Now the height instead of 1 is 1/2. So what is the height going to?
0.
Yeah, but really it's a change in x. Now, what do you call an infinitesimally small delta x? Keep going. You're almost there. It's in calculus.
Take the limit.
Into calculus perspective. What does infinitely infinitely big? Calculus does that.
Because
There
ours
you
is
go.
we got it.
What's your answer? I want an answer, a numerical answer.
Oh.
Give me the volume.
Oh.
I want you to give me a number. What is the volume of that thing? It's a number. So, Tyler said integral. That's true. Infinitely small, infinitely many is an integral. An integral, that's what an infinitely small, infinitely many does, yeah?
Yes. And then dx, dr. Would it be dx or dr?
Neither.
Dx. Okay, we have an answer. Wait, I'm not done yet. I'm not done
You
yet.
have an answer.
Let's see if she agrees. I got it. That's what I got.
Okay, let me give you a little more direction. Pi is pi. Go back to your picture. What's the radius in every case? Here's the r. Here's the r. Where am I going up to? So the radius is the function. Now what's h?
Dx.
The x. And what are the bounds?
0 to 9.
0 to 9. So the volume of this, I would have to sum many cylinders. The function in this case is root x, yeah? That radius is squared because pi r squared h after all, from 0 to 9. So what is the antiderivative of straight up x? 1/2 x squared from 0 to 9. The volume is 81 pi over 2. That is the volume. Okay, now then, a basic analogy of calculus is that you could say area under a curve is to, or leads to, or comes from infinite rectangles as volume of revolution is to infinite cylinders. And both involve integration. Now then, what we just did then is we said the volume of revolution is the sum of many pi r squared h's. And when you revolve around x, the radius is the function, and the height is dx. Are you with me? Now, obviously, helps if you memorize that, but memory comes and goes. If you understand it conceptually, that's it. You with me? All right, then. Let's try one or two together without all the development, just going straight to it. I expect a sketch every time. It doesn't have to be a great sketch. Do your best, but I do expect a sketch. It'll pay off as we go through. Find the volume of the solid generated by revolving the region enclosed by y equals x squared. Oops, that's already a terrible problem. From -2 to 2. Around the x-axis. Now when you take that region and revolve it around the x-axis, what kind of reflection would you get? Well, draw the reflection. and then make the outsides ellipses. That's my pictures. My pictures are usually pretty good, but it's terrible. So you get some kind of a bow tie or a TIE fighter kind of figure if you're a Star Wars person. You with me? Okay. So, how do I find the volume of them? There's lots of these little disks in here. This is called the disk method. So we're just going to sum many disks. There's lots and lots of little disks. So its volume is, come on, the integral of pi times x squared. The function is the radius. And radius squared then is the function squared. So that's x squared squared. The x from? -2 to 2. Cool. All right. Pi can be brought out front. What's the antiderivative of x to the 4th? 1/5 x to the 5th from -2 to 2. So let's call it pi over 5 out front now. And what is 2 to the 5th? 32 minus what's -2 to the 5th? -32. And so you get 64 pi over 5, yeah? Please write yourself a note here. Volume should never be negative. If it is, you did something wrong. Likewise, 0 would be unlikely here as well. All right? This one will be calculator active. This will get a little messy. All right. But first, we can draw it without a calculator. So would you sketch the two graphs, please? There's the old parabola. What is negative? What does negative x plus 6 look like? It's a line with what attributes? Up 6 and a slope of down 1 over 1. All right, so we have a region like that. Yay? Now we're going to revolve that around the x-axis. So do a reflection of that region. Oops, I did it the wrong way. Okay. Do a reflection of that region. And we're going to find the volume of this figure, yeah? Okay, so it would be kind of wacky figure like that. With me? Okay, cool. Wow. So remember, keep in mind that what you're really doing is finding many of these disks. Okay, assuming many disks. So here we go. The volume we know is the sum of many pi r squared h's, and the r is, now we're getting a little more comfortable. What is that picture? That's terrible. What is that? So it's like this. What that? I misidentified the region. My bad. That would have been a washer, which we haven't done yet. Sorry. I didn't read the problem thoroughly. Here's the graph, yeah? And here's the line. But what I failed to read then is the region between those two, enclosed by those two, and the x-axis. So, where's the region? This is the region. I'm so sorry. That's terrible. That would have been a totally different situation. All right. So, this is the region that we're revolving. If I revolve that region, that's a lot of disks, yeah? Now, if I were finding area, how would you approach the area? If you were doing area, you would do right minus left. That's true because it would be one integral. If you had to use x, how many integrals would you need? 2. Do you agree that if you're doing area, you get two different rectangle situations? Do you agree? Now, when you revolve that, then you're going to get two different cylinder situations. So what are we going to have to do? We're going to have to do two integrals, yeah? One for the region that's revolved by the parabola, and one for the region that's revolved with the line, yeah? Okay, so this is the parabola revolved, and this is the line, region revolved. Are we cool? All right, so what should we do next? I kind of have a feel for what I'm going to do. Now what do I do? Yeah, we probably need to find the handoff point. So how do we find where the bounds are going to start and stop? Yeah, we need the intersection points to set them equal to each other. X squared equals negative x plus 6 is x squared plus x minus 6 equals 0. How's that factor? Plus 3 minus 2. So the intersection points are negative 3 and 2, but the region, or the one that pertains to us, is 2. Okay? So the first region, the left region, goes from where to where? Put pi up front. Where to where? 0 to 2. And something squared, because it's pi r squared. What's squared? X squared, yeah? Then the next region is pi, and then it'll go from 2 to 6. Why 6? You're right, 6. Yeah, that's the 0. That's where that line that started at 6 and went down, went over 1, down, went over 1, would hit the x-axis, yeah? So 6 is correct. Radius squared, what's the radius now? Negative x plus 6. Okay, cool. Integrate by hand or by calculator? All right, throw it in your calculator and give me an answer. I can tell you the most common error for people that know what they're doing is forgetting to put in the pi the first couple weeks. So make sure that you remember to type that in first. Don't say to yourself, oh, I'll put it in later. No, you'll forget. So type it in. Don't forget the square, obviously. I am getting 87.1268. How about you?
Yes.
Okay, cool. Cool. Roughly 87.1268 or 126 or 127, both of them. All right. Would you write yourself a note? I know it feels like it's so wrong to leave it without units, but don't worry about units. Now, this is one of the few times where I will put AP above good math. On the AP test, they don't have a point built in for units. That said, so if you leave them off, you aren't penalized. That said, if you put on the wrong units, they do take off. So by putting on units, you can only lose, you cannot gain. So in terms of test strategy on the AP test, we're just not going to put on the units, okay? But what would the units be? Units cubed, because it's volume. Now, this is usually a multi-part problem. You find the area of part A, the volume of part B, and a different type of volume in part C. If you get your units squared and units cubed mixed up, then they take off. So we're going to leave the units off, okay? I know it feels wrong, but it is what it is. All right. Now, consider, is this the next part of your notes?
Yeah.
Okay, cool. Consider now, just like we could do area with y, you can do volume with y. Let's look at that region again, but now this time I'm going to take the curve in the y-axis and y equal 3. So it's not that lower region anymore. Now it's that upper region, you see? And we're going to revolve that around the y-axis. So if this then gets reflected over here, the reflection would look like this, and in terms of giving it perspective, the volume would look like that, yeah? Now, when it's around y, you use y rectangles. How do y rectangles go? Yeah, they go right to left. Y rectangles go right to left. So would you draw maybe 1, 2, and by rectangles I mean super thin, like just a line kind of rectangles, yeah? If those get revolved, then that is your cylinder. And there are actually infinitely many cylinders there. Think like a bunch of coins stacked, yeah? You with me? All right. Now then, it's still the big idea of pi r squared h, but now the radius still is how far do we go to the function? I think you'll agree. Do you agree? All right, so I'm going to call that f still, but leave it blank inside for a second. But what about the height? Now the height is this way. And that's not a small change delta x, right to left. Now height is a small change up and down. So now height is delta y getting smaller and smaller until it becomes dy. So when you go around y, you need to put the function in y terms because you're going to integrate with respect to y. And the limits, instead of left to right, which are an x region, we go lower to upper, yeah? So if we were to find the volume of this, we'll put the pi out front. What are the bounds? Are they 0 to 9 or 0 to 3? 0 to 3. Those are the y values, 0 to 3. And what about the function? If y equals square root of x, then what's the function in y terms? Y squared dy. Cool. So, what is the antiderivative of y to the 4th? Again? 1/5 y to the 5th. From 0 to 3. What is 3 to the 5th? 3 to the 4th is 81. So what? 243, yeah, 243. Okay, so the volume is 243 pi over 5. And we're good to go. All right, so when you do around the y-axis, the volume is pi times an integral of a function of y squared dy from low to high. When it's around y, use y. Try the next one then on your own or with your math amigos. Sketch is required. What do you think? Still working, sorry. Your answer? 8 pi. Okay, cool. Alrighty, now let's talk about this. Actually, take it back. What questions do we have on last night's homework? I think in the interest of time, I'm going to skip to the very last one, okay? Actually, let's just kind of set up this one, and then we'll skip to the last one. Say you graph this again, this situation, like this, and they said, and the y-axis. So the region would be this one, yay? Do you agree? Sometimes when you go to make your graph, you might actually get the region and then erase the rest so it doesn't get super congested. Okay. Now, if you revolve this about the y-axis, what kind of work would you envision? First of all, tell me what variable would you use to go around the y-axis? You'd use y. And what kind of integral situation would you have? You would have two integrals like we had before because we have two different right minus left. So we'd have to find the intersection point and set up two. Do you agree? Okay. And they would be functions of y. All right. I think that's good enough. What would the lower one be? The parabola in y terms or the line in y terms? Parabola in y terms. All right. This is more and more common, especially on the AP test. It's less just mindlessly cranking out the formula and more really actually understanding what this idea is at heart. So you have this vase, and it has cross sections that are circular. So it's kind of like a volume of revolution, yeah? Now, in estimating the volume of this, I believe they let this be the origin. And at different heights, they estimated the radius. Now, let's start with saying the top height is 8. Would you then half it and call it 4? Then half that and go 2 and 6. With me? All right. Now then, if we were to, they have the radius at each of those points they found or estimated the radius. You follow? All right, now we could, based on the table, estimate the volume of the vase by thinking right Riemann sum like rectangles, but revolved rectangles because we're doing volume, yeah? So let's draw this a little better. It says a right Riemann sum. Now, I know that, first of all, kooks me out because this isn't going right to left. You agree? So instead, think this way. When I use a right Riemann sum, which height would I use for my first radius? The one at 0 or the one at 2? 2. So this is going to be my first radius. So think of this as your first rectangle, but revolved would be a cylinder. So that green cylinder is my first estimating cylinder. You with me? All right. And then from 2 to 4, I'm going to use 4. So here is my next cylinder. I would, just like if I were using a rectangle, I would draw the height at 4. This time I'm using a radius at 4. So that would be a cylinder. It looks like the green one was going to overestimate, but now the red one's going to underestimate. You follow? All right. What about the next one? We should draw the radius at, or the cylinder at 6. And so the cylinder at 6. And then last, the cylinder at 8. Yeah? Now, here's where we, just a lot like we do in our work with rectangles. We say the sum of many, the true volume, pi r squared h, can be approximated by several finite cases, yeah, and it is important that you say this is an approximation. The first one is going to be pi, and the radius is the height at what? 2, and that needs to be squared. And what is that? Now that really represents the first radius. The radius we're going to use is what the radius is at a height of 2. You with me? What's the height? 2, yeah? It's from 0 to 2, yeah? Okay, so 2. The next cylinder, pi, and the radius, the second radius, is the height at 4, and then times a height of 2, and then pi height at 6 squared. You can see that once you get your bearings, things start to flow quickly. You got to go slow to start. And then the last is pi h at 8 squared times 2. I think you'll agree that this is a case where they're equal subintervals, so I can factor out a 2 and a pi, yeah? All right, now we just start rolling. I did my job. I went slow communicating what the heck I was doing. Now we roll. What is the height of 2 at 2 squared? 16. What is the height at 4 squared? 9. What is the height at 6 squared? 4. And what is the height at 8 squared? All right. Therefore, my estimate is 2 pi times, how do we got there? 25, 29, 38. Yeah, so our estimate is 76 pi. Let's include units here. What are the units? Inches cubed. Now, in the AP test, they would say in the question, I want you to put in units, indicate units of measurement. Are you with me? All right. Last but not least, say then that instead of a table, I actually gave you an equation for what the R is depending on what the height is at any point. So this equation says, all right, based on you're saying the height is this, you could plug in the height of 0.2 and it would give you the radius. So this equation gives you radius as a function of height. Okay? Given that equation, how could you find the perfect volume? Now, it's so ugly to put in the calculator, we probably want to put it in a calculator. So just talk to me. Pi r of h squared d h. Limits of integration? Would they be 0 to 8 or 0 2 to 3? Yeah, what's the variable? If I were to write all this out, what's the variable in the problem? It's h, yeah, so they need to be h values 0 to 8, this right? And that would give you the perfect. That's really adding tons and tons and tons of little solutions. You with me? All right, cool. That's it. Homework. I think there's only one replacement question, if I recall, and it looked like this. For V at 3, I have negative with work. I said V at 3, V prime at 3 is approximately. Make sure you have that. Make sure you show where or what you did to get your answer. You should say what's the change between 2 and 4 to estimate the instantaneous change at 3. But I got negative 6 feet per second, or feet per second squared. You with me? The units are often a problem. Look back at your work for the units. The velocity is feet per second. The bottom is seconds. It's got to be feet per second over seconds for the ratio G. Yeah? All right. For this, with work, I had 3 is my estimate. Yeah? And the meaning of that is, what do you get when you integrate velocity, allowing for right and left movement? Is that distance or displacement? That's displacement. The displacement from time 0 to time equal 11 seconds is positive 3 feet. You could maybe say it even better by saying at time equal 11 seconds, the thing is 3 feet right of where it was, or 3 feet forward of where, I didn't give you electrical one. There we go, 3. How many times, if any, must the person be at rest? I bet I'll get even the best of you with a little small distinction. How many times did you say? 2. You would not get credit on the AP test. It is not 2. It is at least 2. At least 2. And that is really important. You are given a table. You don't know what's going on. It could be moving backwards and forwards a million times. You don't know. It's at least 2. At least 2. With a whole lot of IVT work, yeah? Is it the idea you're showing that velocity could be 0 in 2 regions? What 2 subintervals could you have a 0 velocity and therefore at rest? And 2 to 4 and 4 to 7. So you would have good work showing IVT, and the keywords would be at least. With me? Other questions? Number 1? 2? Okay. All right. 4? Okay. Yeah, so we might, tomorrow's an extra practice day, so we might finish these questions tomorrow. So let's just do the best we can and do quality work, and if we don't get to it, I'll find. I believe in number 1, this is a problem every year. It's a tough problem. You have a square that the area has to be at least 100, yeah? If I recall. Okay. Don't think they're adjoining fields. They're not next to each other. They're totally separate. So the other one is x by 2x, and the area of that has to be greater than or equal to 800. And I believe the perimeter of the fence is 340 that you have to work with, yeah? All right, and at the end of the day, it's an optimization problem. You're trying to maximize, I don't know if it's meters or feet. You're trying to maximize the area you can get out of the regions, right? And the answer is communism. So we'll talk about that in a second, but now let's talk about A. How do you bound X? What is the max or min X going to come from? Let's talk it's X or Y? What was A? Find the domain for X or Y? X, okay, cool. Where's the min X come from? Why can't X be 0? Because then the area would definitely not be 800, yeah? So the min X comes from the area of the rectangle needing to be greater than or equal to 800, yeah? All right. So that implies that 2x squared must be at least 800, which means x must be at least 20, yes? Yes?
Yeah.
Okay, cool. The other one is much harder, harder to come up with. The max x. Why can't x be infinitesimally large? There's 2 really things going into that. Why can't x be too large? Okay, so there's a fence requirement. The fence is limited. It's only 340. And can I use all of that for x? No, I have to use some of it for y. So let's talk about that. Wouldn't I get the greatest possible x when I use how much y would I use? If I want the biggest x, then that would mean the least y. All right, so let's talk about that. What's the least y? 10. Do you agree? Now, if the least y can, all right, we'll finish tomorrow. And it's not due today. Have a great day. Is that homework stuff go around? I had a homework stuff.
Yeah.
Super. Oh. Have a great day, people.